Good morning, dear students. Last session we have talked about three-hinged stiffening girder to introduce to you and the procedure to solve three-hinged stiffening girders, right? So first we have to take up the free body diagram of the cable. Then you have to take the free body diagram of the girder, three-hinged stiffening girder. Then you have to apply the equations like moment equation at one end and also moment equation at the internal hinge. Then try solve the problem. See, these are all the problems that appeared in the JNTUK in previous years. Okay, so all are of very similar type. So that's why I'll take one of the examples that you see October 18. You will see this span 120 and the sag 12 meters and girder of 40 95 100 120 meter span, right? 25 meters at 25 meters 240 kilonewton load, and from right 40 meters it is 340 kilonewton load. The same is appeared in May 18 also, right? So I'll just take this example, and all other examples are very similar. So number 15, you have one more example, one more unsolved problem. So let us try one example, then you try the remaining. Okay. So these are some short answer questions like what are stiffening girders and discuss. This is what we have discussed in the earlier session. And derive the general cable theorem is for 10 marks. Okay. Right. So let us take this example, and I'm not going to take the same problem. It will be of very similar, okay, in nature. So most of the data is very similar. So you can see that this is the example I'm going to take. Same span, 120 meter span, okay. So the span here is 120 meters. This is the cable portion, main cable. Then this is the hinge at A, hinge at B. Then hinge at A dash, I'm calling it. This the support, corresponding support on girder, at B. I call it as B dash. So C is a point on the cable where the maximum sag is there. The same corresponding point on the girder is C dash, is an internal hinge. So you can see 240 kilonewtons from on the girder, 25 meters from left, and 300 now instead of 340 in the question paper, JNTUK 18 paper. It is 340 kilonewtons. It is 300 kilonewtons. We have taken 40 meters from right. Okay, so this is how the total problem is. Just only change is the load 300 kilonewton instead of 340 we have taken. Okay, right. So these are the free body diagrams already drawn for the corresponding problem. Okay, so the problem that you have seen is this one. This is a problem. So we have separated the cable. So which means that what you need to do, there will be suspenders in this. Okay, like this. There will be suspenders connecting the main cable and the girder. Okay, so you have to cut all these girders. Okay, all these suspenders you have to break so that you can free the cable from connecting to the girder. Okay, so that is what is done, and this is the free body diagram. So because you are breaking, you are have a section at this location. This is the section. So that's why I can see the force in the suspenders. Okay. So large number of closely spaced suspenders. Hence, we consider that as UDL, which is of Q naught is the quantity. Okay, right. So this is the cable free body diagram, sag 12 meters, and all these are suspenders. So this is like we are assuming this as UDL, okay, of quantity Q naught, because you don't know the load. It is like internal force in the suspenders. What is UDL? It is internal force in the suspenders, like tensile force in the suspenders. Okay, now this is a free body diagram of the girder, three hinges. Okay, so where the hinge has to be removed, and you have to apply vertical reaction. This vertical reaction. Okay, so what are the forces acting on three hinge stiffening girder? So this is the three hinge stiffening girder. What are the forces are there? You see VA dash, vertical reaction at the hinge, vertical reaction at this hinge, VB dash, and applied load 240, applied load 300, and UDL of Q naught from suspenders. Okay, these are all connecting here. The girder and the main cable is connected by suspenders. So that suspenders, if you break them, you can see the UDL. Okay, so these are the loads acting on it. Okay, so first step one, what you need to do, take the free body diagram of the stiffening girder, then apply sigma MB0. This is the first thing to do. Sigma MB0. Got it? So draw free body diagram of the stiffening girder, right? So applying sigma MB0, this is sigma MB0 applied. So VA dash into perpendicular distance 120, VA dash into 120. So clockwise positive is considered. Next Q naught, Q naught into, this is Q naught. Okay, UDL. Q naught into 120 will act at the middle. To distance between the point load converted into between the point load converted load into and the support B is 60. Okay, so 120 Q naught into 60. Then the other two loads, 240 into 95, anti-clockwise taken minus 300 into 40. Right? You see, VB dash is going to become 0. Moment from VB dash is 0 because moment center is at B dash. So VA dash, support reaction, uniformly distributed load from suspenders, applied load 240, applied load 300. So you have equation in terms of VA dash. VA dash 60 Q naught is equal to 290. So this is one equation, right? Right. Now take section in the stiffening girder. You take section in the stiffening girder where at internal hinge. So take a section at the internal hinge like this. Take either left or right, which is useful for you. So we have already VA dash Q naught equation. So if I take left part, it will be useful for me because I will get VA dash and Q naught in the equation. If I take right part, it is not useful for me. So take the left part. So this is what is the split in the stiffening girder. This and these are the split. Okay, stiffening girder is split into two. Okay, right. So left part is considered, and now again you apply moment at C is equal to 0. Moment at a section. Okay, so that's why you will have the sign convention nature, right? This is how it is. Sagging positive. So left of section clockwise, right of section anti-clockwise, both are positive. The same is applied here. So VA dash into distance is half distance, 120, half of 120, 60. Okay, right. Plus uh, same left clockwise, Q naught. Q naught is upward, you see. Don't think that the UDL, as we have assumed this as UDL, it will be downward. Okay, it will be upward, right? So 60 Q naught into 30, half of the distance. Half of 60 is 30. Okay, and only one load is there because the 300 kilonewtons falls to the right side of section. So to the left of section it is 240. So 240 into 35 is anti-clockwise, so minus equal to 0 will give you another equation in VA dash plus 30 Q naught is equal to 140. This is equation number 2, which is to be used in solving 1 and 2. If you solve, you will get Q naught value as 5 kilonewton per meter and VA dash as minus 10 kilonewton. But if you apply sigma Fy0 for the girder, once you get VA dash, you will get VB dash value. VB dash is total load, okay, total vertical load, okay, 50 kilonewton, right? So Q naught is 5 and VA dash minus 10, VB dash minus 50. Means what? The direction of VA dash and VB dash should be reversed. Okay, right. So this is regarding the finding reactions on the girder. So there are three reactions on the girder now, like support reactions and also reaction from the suspenders. This is extra added. So three reactions we have found: Q naught, VA dash, VB dash. Now come to the cable free body diagram. Cable free body diagram. So VA, H, VB, H, and Q naught. Right. So Q naught is solved. It is 5. Okay. Right. See here. This is solved, which means this is also same. Right. Because this is a cable. The force in the cable is same throughout. So Q naught value is solved. So you need to solve for VA, H, and the tension value, all that. So because the cable with UDL case, we have already know the horizontal thrust, how to calculate, okay? WL square by 8H. If you see my previous lectures on this cables, you will have this equation WL square by 8H. Here the W is Q naught, so W into L square by 8H. So Q naught value is 5 and L is 120, 120 square. So 5 into 120 square divided by 8 times H means the sag value 12. Okay, so this will give you H value, horizontal thrust 750 kilonewton. Okay, and anyhow VA is equal to VB because only UDL you have. It is total 120 into Q naught. So 120 into 5. Okay, so 600. Half of the load goes to the left support and half of the load goes to the right support. So 300 is the vertical reaction value. Either this or this will be 300 kilonewton. And horizontal reaction is 750. So what is the tensile force at the support? It is like resultant of this and this force. Resultant of this force and this force will be the tensile force in the cable, maximum tension. So maximum tensile force occurs at the support. This we have talked about in when we discussed cable, right? So square root of H square plus either VA square or VB square, both are same. So 300 square will give you tensile force in the cable maximum at support. That is 807.8 kilonewton is the maximum tensile force in the cable which occur at this support. Minimum tensile force will occur at this location at the maximum sag point. Okay, so here the minimum tensile force occurs, and that minimum tensile force is equal to H value. So minimum 750 kilonewtons will be there in the cable, maximum 807.8 will be there in the cable, right? And if it is, the question is to find the shear force and bending moment in the girder. So you know all the reactions. You see, 10 downward, 50 downward. This is like 5 kilonewton per meter upward. Do not forget 5 kilonewton per meter upward UDL. So if you try draw shear force diagram, so downward 10, so this is the reference line, right? So come down by 10, right? Then what will be the force from here to this is 25 meters, 25 into 5, okay? So 125, so you have to go up because upward, so go up by 125. So you are down by 10. So 125 minus 10. So 115 you have to reach above. Then there is downward 240 there. Okay. So 115 minus 240. So it will be minus 125. So down 125. Then again, right, it is 35 meters into 5. So that you have to cross till this 300 you have to calculate. So total 45 meters between this point and this point. So total 45 meters. So 45 into 5 is the load. UDL is 5, right? 225 is the total load. So you are down by 125. Okay. So if you want to reach upward 225, you have to come and reach 150. So 150 plus 125. Okay. Then this will be 150 here. Then if you come down by 300, it will be 150 down. Then again from here till this 40 meters. So 40 into 5 for 200. So you have to go up by 50 and downward 50 is there. So you will reach 0 there. Okay. So this is SFD that we are going to plan. Okay. Got it? Right. What about BMD then? BMD, just like your beam to draw BMD. So 0 at the end, then everywhere UDL is there. So it is all parabolas, matter of parabolas. So try take section between this. Okay, sum of all moments to the left. You have to write mx equation. Substitute x is equal to 0 and x is equal to 25 to get this value, and you will have point of contraflexure crossing this, so that you have to find by making mx equal to 0. So this is all like drawing BMD for a beam. It's like a beam. Girder is nothing but a heavy beam, right? So this parabola shall reach 0 and then going for 0 here. So likewise you have to take different sections between different parts. So between A dash and the point load, and between point load and C dash you need one more section. Write MX equation. Between C dash and 300 one more section. Between 300 and 50 one more section. So you need to take four sections and you have to write four moment equations. Then you are able to complete this BMD. Okay. So you have one, two, 3 point of contraflexures, and where this C dash bending moment is 0, it is already known value because C dash is an internal hinge. So this cannot be considered as the point of contraflexure. So only where the bending moment cross the value from minus to plus only can be considered as point of contraflexure. So here, here, and here. Okay. So 3 point of contraflexures where C dash is a physical hinge, it is not imaginary, right? But other three are imaginary hinges. This is imaginary hinge. This is imaginary hinge. This is imaginary, but this is real hinge, real, where you provided in the girder. Okay. So this is how we solve the three-hinged stiffening girder problems. Okay. So take the free body diagram of girder first, then apply equilibrium equation at one end, then take the section at the middle where hinge is there. Take one of the parts which is useful for you, and then write MC is equal to 0, solve, get one support reaction and Q naught value. Then take sigma Fy0, get another support reaction. So there ends the matter with the girder free body diagram. Then come back to free body diagram of the cable. Okay, then solve for H value, horizontal thrust in the cable, and also support reactions VA, VB. Once you solve them, then you are able to get maximum cable tension at the supports. And then after that, if you are asked for SFD or BMD, again you go back to the free body diagram of the girder. Then you treat like as a beam, treat it like as a beam. Okay, draw SFD and BMD, just like your uh, shear force and bending moment studies. Okay, right. So try practice all these questions that you have to practice such questions. Then only you will be comfortable with this procedure. Okay. So you have one, two, three, four, five problems to practice. So take these problems for your practice. Then try put your answers on a white sheet. Okay, so get ready for the tutorial sheet submission on this cables and suspension bridges. Okay, right. Thank you. Next session we will talk about two hinged stiffening girders in the suspension bridges. Okay, right. Thank you.